So this is my project, CyberEther, that I do in my free time. Maybe you just saw it on Twitter, like the cool tweet about processing signals. This is the third consecutive year that I do updates on the CyberEther project. As I said, it's free time only, and I do these things because I like it. So this year, I want to talk more about the bridge to portable GPU accelerated interface. Like, how can we, I say, CyberEther interface with other programs more efficiently and better. And one of those key points is documentation and explaining to y'all how CyberEther works really. So I thought I would give you a brief why I did CyberEther and why I think it's important. So CyberEther, for those who don't know, is a multi-platform GPU-accelerated interface for compute-intensive pipelines. So in other words, if you have lots of data being generated in real time, and your amount of data generated in real time is very high, you want some way to visualize that it will not slow down your processing, your data generation. And from all the years back, for example, here in M3 from Apple Silicon, you can see here with semi-analysis charts that the CPU part of the M3 is just the red part on top of there. So almost everything else, some structures are shared with the CPU, but the blue one between the SLC cache, it's all the GPU. So when you're running your application on the CPU, you're leaving behind more than 50% of the die in this circumstance here. So it's my pitch that modern software with modern requirements needs to support in some way heterogeneous computing to make sure you're utilizing your machine to the full extent. So that's why I started CyberEther, just to show how this thing can be done. One of the ways, there are many. There's a bunch of points about CyberEther that I want to discuss today. One of them is the render. So CyberEther is made for multiple parts. One of them is the render. So the render is basically, it's not using any dependency that you figure out for like interfacing, like Qt or others. It's fully implemented using Vulkan and Metal and Web GPU. That's why it runs in a variety of places. I also want to talk about the computer scheduler. That is very important in conjunction with the visualization, because sometimes your visualizations needs to be coupled with the presentation because they need to be synchronized. For example, if you have an input like a time domain IQ sampling and you want to plot that in a frequency domain, you need to do the FFT. You can do that before passing to CyberEther, but CyberEther really makes it easy to do together with the presentation. So it's more efficient, can be more efficient. And also, it has native browser support. So the same code that is running natively on your computer can be compiled using WebAssembly. The same C++ code with just a few, like three assertions that and it can be run on the browser. So the browser is interpreting the WebAssembly and running C++. And the render utilized when you're in browser is the Web GPU one. So Jetstream render will abstract away the APIs, graphical APIs, Vulkan, Metal, Web GPU. You just need to code once, your element once, your line once, for example, and it will run on all three and can be selected in runtime, whichever you want to use. For example, if you're in a MacBook, you can choose Metal or Vulkan to run. It also has a low latency, headless remote interface. So you can receive the data, process the data, and instead of shipping the data out of your computer to the place where you want to visualize, you can just send the frame buffer of CyberEther to another location. Another thing, this is completely new for this year, Superluminal, is a higher level interface for visualization that is for Python and C++. It reuses CyberEther components, but with a much nicer interface where you can implement it on your project in minutes. And It's MIT licensed, so there would be on slide. So the graphic interface here. So you can see CyberEther runs on top of it. CyberEther is the modules plus the compositors. And the compositors, the modules, for example, has the presentation part and the compute part. And the presentation part is the render interface with Vulkan Metal Web GPU, and then in talk with the GPU. We also need to have the abstraction of the view part, so you can actually show the frame that you just rendered on screen, and each platform has their own implementation. GLFW does some work to make this as cross-platform as possible, so that's why we use that for Linux, Windows, and Mac OS. But for something like iOS, you need to also to use another thing called MTK view, so you can show the frame buffer on screen on an iOS, iPad OS platform. And also, of course, just I described, the headless one that do not depend on your system having a compositor. So you can just render in a memory space on your GPU. And then if you have on a NVIDIA GPU, you can encode that on hardware on the same device, or use software encoding if you're not. And the render supports multiple advanced features that are new for this year. One of them is font rendering, so you can draw text on your plot in a very efficient way. With instancing rendering, that is, if you have the same element multiple times happening at the same element happening multiple times, instead of having a vertex buffer repeated, you can just tell the render to repeat those at certain locations, so you don't need to spend memory, and your GPU can do batching processing to draw everything faster. And also multi-draw indirect, so you just issue a single draw call and we'll draw multiple different elements at the same time. So both of those were needed to implement font rendering, and that's what's new in beta alpha 5 version of CyberEther right now on the GitHub. And all of this gives you freedom from proprietary or stuck-in-time render interfaces. I won't name any one of those, but you all know some hurdles you have when you're trying to deploy some kind of interfacing. You're either limited by the platform you're running at, or constraints of the structure they use. So I went in the path of writing my own. And like I described, we have 3 different implementations of the render. So the Vulkan one are mainly used for Linux, Windows, and Android, including MetaQuest classes. I plan to add support for that by next year. Metal, that works on Mac OS, iPad OS, iOS, tvOS, all of them that has a GPU. And nicely also the web GPU one that works on Chrome, the latest version of Safari technology preview, and Firefox nightly in some platforms. So they all share the same code, and they all fully featured versions of each other. So to make more assertion to it runs everywhere. It runs on a Linux machine, it runs on Windows, it runs on Mac, it runs on Chrome, it runs on Safari, it runs on iPhone, it runs on iPad, it runs on MetaQuest. No different code necessary. It runs most of the places. If it has a decent GPU made in the last 7 years, probably it will work. You just need one of those APIs, and it should work. And no tricks here. It's the same code running everywhere. So another thing that I found nice about CyberEther is the remote headless rendering. So this is a flowchart of how it works. So for example, you can have a computer with a sensor producing 12 gigabytes per second of data, and you need to visualize that. You would probably need to chip this data out of the computer to do a flow graph on your computer that has a screen, or use terrible VNC that are very hardly accelerated by hardware and have a 1 FPS read back from your data. Or you can use CyberEther with the headless interface. So a CyberEther instance is running on the server that is receiving the data. The CyberEther is rendering the data on a frame buffer. That frame buffer, the headless viewport that I'm talking about, is compressed using H.264 or H.265. If you want a lossless conversion, you can also use FFV1, that is a lossless codec that does a good job, but not as efficient as H.265, 4, and 5. And then instead of shipping out 12 gigabytes per second, you're shipping out 25 megabits per second that can be easily sent over a bad channel. And that's not the VNC compressed image is like 1080p 60 hertz out of your computer. And then another CyberEther module will receive that frame buffer and will draw on screen. So it's the experience, if you don't know, it's running in a headless interface in a fairly low latency interface. You won't know that's a headless instance of CyberEther. Another advanced render feature, the line plots before were rendered with a single line, but now it's rendered using a polygram. So you can choose the thickness of the line, and that's very important. I mean, how hard can it be to draw a line with OpenGL, Vulkan, etc.? Turns out very hard. Marcus knows about this. It's easy to do it, but it will look like crap. But if you want to look nice with nice anti-aliasing, you need to really get creative. So these lines now support signed distance field. That's a technique to make the edges of the line smoother, so it doesn't anti-alias much. The worst ones are like diagonal lines. That's pixel steps that makes that stair stepping that is very annoying to see. The signed distance field, or SDFs, make that much better. And also, it can run a multi-instancing support that I just described, that you can run multiple elements at multiple places, the same element in multiple places. Multi-draw, different elements in multiple places also. And also, everything, so every open web GPU, Vulkan, and Metal uses different shader languages. Metal uses MSL, Metal Shader Language. Web GPU uses WGSL, and Vulkan uses SPIR5, that is the intermediate conversion thing. So what CyberEther does is you need to write a GLSL shader. CyberEther will compile that to SPIR5, and then the SPIR5 will be used for Vulkan, and the SPIR5 will be transcoded to MSL or WGSL automatically for you, so you don't need to write 3 different shader languages for each backend, so you can all share one. And also, the thickness of the line, all the polygons, are not rendered by, it's not calculated on the CPU. There is compute shaders before the presentation shaders that you can pass just an array of points in space, and that shader will do the thickness, the right thickness for your viewport, calculate all of that, and send directly to the presentation shader. So there is no time wasted on the CPU, and that can be done on the GPU with very good parallelization. So this is the computation part of the CyberEther. So you have modules, just like as last time. And then there's the heterogeneous API scheduler. So you can use Vulkan, Metal, CUDA, Web GPU, or CPU to process your data. There's no vendor lock-in. You can, if you have a very exoteric language that you implemented yourself on your very large FPGA that you bought from Microsoft for $10, you can do it fairly easily. Just create a new graph on CyberEther and implement your own language. It supports all major computational. I want to add cycle, but I don't have time. And also it facilitates, so the problem with running multiple different compute APIs at the same time, that they don't talk with each other most times. So you need to do some very clever things for synchronization between them, because if you send a kernel that is executing asynchronously, you need to wait until that API finishes the work to start the processing with another API. So CyberEther, when you're using modules, will compile that, will abstract that away from you, so you can mix and match any kind, multiple types of blocks. You can put like CPU, CPU, GPU, CPU, and all the synchronization dispatch will be done transparently, handled by the scheduler away from your. And also transparent memory sharing between APIs and devices. For example, if you allocate memory with Vulkan, you can't use it directly with CUDA unless you're using CyberEther, or if you write like 500 lines of code to make it work. CyberEther, it's much nicer way to, if you allocate memory with CUDA, for example, you have the first line there, you allocate an array of float 32s on CUDA. You can check if it's CUDA, the root device is CUDA, and the references are one. If you want that, if you want to use that same memory on Vulkan, you can just create another tensor, but this time you play, say Vulkan instead of CUDA, and then you pass the CUDA tensor to the constructor of the clone storage, and then that data will be mapped using CUDA low-level virtual memory management to Vulkan. So that way, you can use the same memory that you're running your compute kernel on CUDA, and you can present that data on Vulkan without having to copy that memory on device. So that makes things much more efficient. And also you can do other way around, from Vulkan to CUDA, and also Vulkan CPU, CPU to Vulkan. Same thing for CUDA, same thing for CUDA and CPU. But there is also the PCIe. In some platforms, CPU and CUDA are in the same socket, so you can share your CPU memory with CUDA and vice versa, but only in some platforms like Jetson. So this is one video here. So this is originally a CPU-based flow graph, and you can see I am changing the flow graphs to green. That means that it's running on CUDA now. You can see on the left there that the kernel of each block are being compiled just in time by NVRTC. That is the just-in-time compilation from CUDA. So our string, that is the kernel, comes into the compiler. Compiler compiles to PTX. PTX gets executed, getting data from the input, and executed, and the data from output. So you can even define, if you have a block that is just like a text box, and you type your own kernel at the time, you can make it work, because you don't need to recompile, because all the CUDA kernel compilation is being done in just in time. And this is the example of everything running at once with CUDA. Even like ranging, amplitude, plotting, and waterfall. So this is more demos. For those who doesn't know, this is how CyberEther flow graph works. So you can just create, like in a radio, just get block, drag the drop the block, and it will create it. Unlike CyberEther, unlike GNU Radio, we can have visualizations inside the flow graph. So there's this cool flow graph itself, and you can see the data there. But if you don't like that, you can also create a window and see it in other places. This is the RFNM. Check out his booth, this in the conference, RFNM, not Magic, running 120 megahertz of bandwidth in a M1 Pro MacBook running on battery, 120 FPS, and being rendered by CyberEther plus the spectrogram and the waterfall. This is quite an older version, but it's still applicable. And this one is the example of like FM demodulation. So we are channelizing the incoming data from SDR to get just a single FM radio. And it's all implemented on the filter engine, but it's basically doing resampling on the frequency domain, taking the data, and then smoothing out the chunks, because when you're doing fur filtering on chunks in the frequency domain, you can have the borders will be distorted. So you need to do a sum and add kind of stuff to make it the audio not popping. So otherwise it will pop every time it crosses the batch size. So that's what this is doing. You can see the whole example in CyberEther. And also, just a demo of that running on iPad. Is exactly the same version that is running on the computer, running on the iPad, and you can use an Apple Pencil to tune your things or move the flow graph. So touch interface, Apple Pencil support since last year. And it's quite nice, to be honest. Quite a powerful chip on the iPad these days. And also, the presentation I gave last time of CyberEther being used by the Allen Telescope Array. So this is receiving 12 gigabytes of data, doing the beamforming with Blade, and with the data being shown on screen in real time. At the time, I was in Brazil, and this was being processed in the ATA, and the compressed video using the headless remote interface was being transmitted from the ATA to Brazil, 12,000 kilometers, 300 milliseconds of ping, and I was still able to run CyberEther kind of nicely with 300 milliseconds of delay, but still I could deal to see 12 gigabytes of data without having to send that to Brazil. So that's the GOES thing, the LTE thing, same thing. And also, a new thing that I just said is superluminal. It's a high-level interface that reuses elements from CyberEther. So my goals with this thing is be high-level, like Matplotlib, but it works on C++ and also on Python with almost the same API. It has high performance for visualization with a certain focus on animations if your data is changing constantly. So this one should be better than Matplotlib for this. And also should have similar syntax from C++ and Python. And it needs to be able to implement in minutes. So this is what I came up with. It's just a single import superluminal as LM, and then you create some data. Do lm.plot. You put your data vector there, your type of plot you want, for example, line or waterfall, and then you label it. And you show it, and then it works just like Matplotlib, but working with CyberEther under the hood, and you can see in the left there the plot being plotted, and you can interact with it. You can do a zoom in, zoom out, just like Matplotlib. Same thing can be done with same example of a sine wave-ish being calculated in the real time. So you start your data, you do LM plot data, and then that data needs to remain the same. And then you do the real-time callback of CyberEther. And then while it's running, you are updating your phase of your sine wave, and then calling lm.update, and your data is updated on screen with the same data. If you have GPU, it's not implemented yet, but if you have GPU buffers created with CoolPy, for example, you can do the same flow, just change your data on the GPU, and it will be plotted on screen without copy, if possible. So also, one thing is that you can use with time and frequency domain. So if you have your data is just a time domain version of your data, and you want to plot the frequency domain, with Matplotlib, you would need to use like NumPy FFT first. With CyberEther, with superluminal, you just specify the domain of the input and output data that you want to plot. For example, if your input is time domain, just say lm.time and output lm.frequency, and superluminal will do the FFT on the fly for you. Same applies when you're doing the animation one. Everything will be handled by by Superluminal. And as I said, it also runs on C++. You can run almost the same syntax. So you create data, you call Superluminal plot, you give a name to it. You can do a mosaic of plots. If you want 2 plots, you just create that array of arrays, and you put just 1, 0, and then 0, 0. Another one, you put 0, 1, 0, 0. Kind of more intuitive than I think. I think it's more intuitive than the matplotlib way to do the mosaic things. Also, you specify the data, the buffer, and so the type of the plot, and then you just show, and it will create the same thing as before. The goals, future goals for Superluminal is to add more visualizations like waterfall, constellation, spectrogram, make installable by pip install Superluminal, just that. It would push down a compiled version of CyberEther, Jetstream, and install in your computer with just a single line of code. That's TBD when I will be able to do this, probably in the next month or so. And I support more types, currently just complex float, but I am planning to put more support there. And support CUDA buffers, like our metal Vulkan CUDA buffers, and add more examples for you guys to be able to make sense. CyberEther and Superluminal are MIT licensed. That's what I have to tell you. If you like it, you like it. If you don't, you don't. I don't know. If you want to do GPL, you can use GPL. I think it's double licensed if you want to. Future work. If you have free time and want to help me doing expanding CyberEther, please help me. I am a single person working on this with my free time. I have limited time, and it's very hard to do this. So a good first issues would be like stabilized browser support. There's some details to be fixed. Create a demodulation demos if you are more into the DSP parts of things, or third-party SDR support. If you are an SDR vendor with her own API and you don't like SOAP SDR, write more tests. Always nice. Expand documentations if you're not a technical person, and stabilize the remote thing, the transport and the protocol. If you have any questions, you can ask me, or you can submit an issue or a discussion at the CyberEther repo, or contact me over email. And thank you for attending.